Okay, so we're going to take a look at exercise number 2 on page 67 of the workbook. And this is another example of the type where we're given a function and we're trying to use the derivatives to give us information about what the function looks like. Okay, now in this particular case, the function that we're starting with is pretty complicated in terms of a formula. And so it would be difficult to calculate the derivatives by hand. So they've actually done that part for us. And in part A, for example, they've taken the derivative, gone through all of the algebra that would be necessary to simplify it, and come up with this formula. We're simply being asked to use that formula to determine where f is increasing and decreasing. Okay, so this process is going to look the same as it did in our previous examples. We are interested in finding critical points to get started. Okay, what's a little bit different here, though, is that this is the first time that we've looked at a derivative formula that has a fraction, where there's a numerator and a denominator, which means that we're not only interested in where the derivative is 0, but also where it's undefined. Okay, so let's start with the question, where is the derivative equal to 0? Well, if you just think back to fractions for a minute, a fraction is equal to 0 when its numerator is 0. Okay, so if you look at our formula for f prime of x, the numerator is 8 minus 3x. So if we set that to equal to 0, it's going to answer the question of where the derivative is 0. And we can solve that equation without too much trouble. Just add the 3x over to the right-hand side and divide by 3, and you're going to get x equals 8 over 3. There's one of our critical points. Okay, but we also get a critical point where the derivative is undefined. And if you ask the question, when is a fraction undefined? It's going to be undefined when its denominator is 0. Okay, so we want to ask the question, what values of x would make our denominator equal to 0? Okay, well, you might be able to answer this question just by looking at that denominator. There are kind of two terms. There's the 3x to the 1/3. Okay, notice that that's 0 when x is 0. So that's one place where our fraction would be undefined. And then the second term, 4 minus x to the 2/3, that's going to be 0 when x is equal to 4. Okay, so I missed a word. So f prime of x is undefined when x equals 0 and when x is equal to 4. Those were the two numbers that made our denominator equal to 0. Okay, so there are 3 critical points in all. And when we make our sign chart, we need to include all 3 of those numbers. All right, so let's make our sign chart. So we'll start with our number line. Okay, we've got 3 numbers. We're going to put them in order left to right. So starting with 0, then we come to 8/3, then we come to 4. That divides our number line into 4 different zones. And we're interested in the first derivative here. All right, and you might remember the next step is to pick some test values. Okay, so we need a number that's less than 0 for that first interval, maybe -1. And then between 0 and 8/3, nice number, there we could maybe choose 1. And between 8/3 and 4, maybe 3. And then finally a number that's bigger than 4, we'll choose 5. Okay, and the idea is to take these numbers and substitute into the derivative. We've done this a couple of times, so I'm not going to go through the details of that. I'm going to let you do that. You're going to take these 4 numbers, plug them one at a time into our derivative formula, and you're going to come up with signs, which I'm going to fill in now. Minus, plus, minus, and minus. And again, you can confirm those on your own. All right, and with those signs, we should be able to answer the question that they're asking us. Okay, where is f increasing or decreasing? Well, it's going to be increasing everywhere that we see a plus sign. And it looks like there's only one place where that's true. Okay, from x equals 0 to x equals 8/3. and then we're decreasing everywhere else. Okay, so from negative infinity to 0, 8/3 to 4, and 4 to infinity. Okay, and there's our answer to part A. All right. And then moving on to part B, similar question, but this time they're asking us about concavity. Okay, which means that we're interested in where the second derivative is positive and negative. Okay, so we're going to repeat the whole process that we did before, only we're going to make a second derivative sign chart now. All right, so we'll break it down into the same two steps that we did. Okay, and let's scroll up so that we've got a nice blank page in front of us here. Okay, we're going to look at our formula for f double prime of x and ask, where is it equal to 0 and where is it undefined? Well, the first thing to maybe notice is that the numerator is negative 32. That's never equal to 0, so there are no places where the second derivative is 0. So that numerator doesn't yield any critical points for us. In the denominator, though, by the same logic as what we did above, x equals 0 is going to make that first term, the 9x to the 4/3, 0, and x equals 4 is going to make that second term 0. All right? So the second derivative is undefined when x is 0 and x equals 4, because those are the two places that make the denominator 0. Okay, so this time we've got two critical points. We're going to make a sign chart for the second derivative now. Those two critical points are going to divide us into 3 zones. Okay, and we're going to pick test values just like we did before. Okay, so a number that's less than 0, -1, a number that's between 0 and 4. We've got choices, but how about 2? And then a number that's bigger than 4, maybe 5. Okay, and this time you're going to take those 3 numbers and substitute into the second derivative. Okay, I'll leave the algebra on that for you. You're just going to take these numbers one at a time, plug them into the second derivative up here. Okay, and I'm going to show you the signs that you should end up when you do that. Okay, a minus, and a plus, as it turns out. Okay, and so now we should be able to answer the question of where f is concave up and concave down. So f is going to be concave up wherever we see a plus sign, a positive second derivative. I see one plus sign, so that's going to be on the interval from x equals 4 to infinity. Okay, and then we're going to be concave down on those two intervals where we see negative signs. So from x equals negative infinity to 0, and again from 0 to 4. All right, and there's our answer for part B. Okay, and then finally, they want us to kind of tie it all together in part C here and see if we can locate local maxes, local mins, and inflection points. Okay, well, this is going to involve kind of looking back at the sign charts that we've already made. Okay, and let's start with the local max and the local min part of this. Okay, there we're going to need to look back at our first derivative sign chart. So we're going to need to scroll up a little bit here. Okay, so looking at the first derivative chart kind of up at the top of the page here, we're going to get a local maximum at a place where the derivative goes from positive to negative. And I see one point like that, this 8/3. There we're going up to down. We're going to get a local maximum there. And any local minimums? Okay, I see one of those as well at 0, because our slope goes from negative on the left to positive on the right. Okay, so we're going to get a little minimum there. All right, so let's go back down to the bottom of the page and state those two answers. Okay, sorry for the scrolling up and down here. All right, so we located a maximum at 8/3. Okay, and a minimum at 0. Generally, when they ask you for a max or a min, they'd like not only the input but the output. So f of 8/3, we'd want to calculate that value. We're going to take that and plug it back to the original function, which you can see at the top of the page. So x to the 2/3, we'll plug in 8/3 there. 4 minus 8/3 to the 1/3. Okay, and obviously that's a job for your calculator. If you plug that in, you're going to get out about 2.12. There's our local maximum value. Okay, and if you plug 0 in to that same formula, you're going to get 0. There's our local minimum value. Okay, and do we have any inflection points? Okay, well, we can see that from our second derivative sign chart, which is sitting kind of right at the upper right-hand corner of our page. We are looking for a sign change in our second derivative sign chart, and notice that that happens at this number 4. Okay, there we go from concave down to concave up, so that should be an inflection point. All right, so we'd take 4, and if you plug that into the original function, you're going to get out a 0. That's going to be an inflection point. Okay, well, we are done with the problem at this point, but I'd like to add one more step. This is instructive when you're doing an example like this, to maybe sketch a graph and see if the graph looks reasonable based on our answers to these questions. Okay, if you have a calculator or maybe a graphing program on your computer, you could actually graph this function together with me. I'm just going to try to draw a very rough graph of this. Okay, and this is a graph of the function that we started with, x to the 2/3, 4 minus x to the 1/3, just as a way of checking ourselves. Okay, so bear with me here. This takes a while just to get all the points labeled and everything. Okay, and very roughly speaking, here's what this graph looks like. Okay, whoops, sorry. I'm still a little bit new to this iPad, so. All right, and remember what I'm drawing here is a very rough graph. I'm probably not going to get it completely right. Okay, well, it kind of has that sort of a shape to it. And the thing I'd point out is that you can see some of the features of our calculations in this graph. For example, we've got a local maximum here. Whoops, there I go again. Okay, and if we've done our calculations right, that point should be 8/3 and 2.12, our local maximum. You can look at the picture and see if that seems believable. And then we also said that we have an inflection point at 4,0 right there. You can kind of see that on our graph as well. Okay, and I'll leave it to you to maybe go up and kind of compare the other answers that we got to A and B to the general shape of this graph. Maybe you could graph it yourself on your calculator to